Okay, I'm going to give a presentation on the interference statistics in random millimeter wave ad hoc networks. My name is Andrew Thornburg, along with my co-authors Ning Bai and my advisor Robert Heath. So why millimeter wave networks? Why are we interested in them? Why do we care about them right now? The main reason that we are interested in them is because of the huge amount of spectrum that is available. This is the FCC allocation cart for networks from 300 megahertz to 300 gigahertz. And as you can see up here, this is kind of what is currently used for deployed wireless networks. All of that spectrum fits in this small chunk of the millimeter wave spectrum. There's another ISM band up around 60 gigahertz with 7 gigahertz of bandwidth. And the FCC is currently undergoing reviews to open up even more spectrum to make it available for licensed communication. And technology advances recently have made it possible for cheap consumer devices. Millimeter wave standards have kind of furthered the deployment of these devices. 802.11ad is coming out soon. And it's applicable to wireless LAN, cellular, device-to-device, and in our case, ad hoc networks. So what is different at millimeter wave as opposed to current UHF communication? One is that building blockage has been shown to severely reduce the propagation of millimeter waves. And what this means is, in the ideal case, is that this will reduce interference. As you can see from the little cartoon there, the two nodes that are communicating are kind of isolated from this interferer that is pointed right at them. And secondly, there's the use of directional antennas at the receiver and the transmitter. Because of the decreased wavelength at millimeter wave, large antenna apertures or large antenna arrays can be built with many, many antennas that allow for directional beamforming. As seen here, the two desired nodes are communicating towards each other. And what we try to answer with this paper is interference significant? Is interference a significant design impairment in millimeter wave ad hoc networks? So there's been a lot of prior work on both ad hoc networks and on millimeter wave. Most of the previous ad hoc network related work for millimeter wave networks has been towards the standards that I mentioned. There's 802.15.3c, which is a personal area network standard, and 802.11ad, which is a wireless LAN standard. And those are primarily concerned with indoor networks. What we are concerned with here are large-scale outdoor networks. And there's been a lot of work with stochastic geometry, which is what we use in this paper, from Bocelli. It was a pioneering work in the early 2000s. And there's also been some prior work with directional antennas. And recently, there's been a lot of talk about interference in millimeter wave networks, whether millimeter wave networks will be interference limited or noise limited because of the large bandwidth. So that's kind of the questions that we tackle here. I'm going to go on to the system model. So here's our general network model. What we have here is what we call the typical node. We assume that the typical receiver is aligned with the typical receiver or typical transmitter. We have a bunch of randomly placed interferers, each with directional antennas pointing in a random direction. And additionally, we have random buildings that are deployed with random widths and lengths and random orientations. And this is our desired signal, and this is our interference. But what we are interested in specifically in this paper is just the interference and the noise. So we are going to be focusing on the interference term and then the noise term. So here's a kind of a cartoon example realization of our random network. So here are those random buildings that are deployed according to a Poisson point process along with the transmitters. The center of each building forms a Poisson point process of independent of the transmitter process. We have a typical receiver located at the origin, and the length and width of the buildings are drawn independently from two independent distributions. And we use a blockage model that determines if each link relative to the typical receiver is either line of sight or non-line of sight. So for this work, we used 3 different antennas, all kind of from the same antenna model, which is the sectored antenna. So what we do is we have a main lobe and then a side lobe. And the main lobe is derived from the measured antenna patterns for a uniform linear array. And the back lobe is determined according to the worst possible side lobe. So it's sort of a pessimistic model. And here now we're going to derive the interference cumulative distribution function in a mmWave ad hoc network. So here's the main quantity that we're going to be working with, the INR. We have the random gain component, which we simplify into 3 possible scenarios. We have the interference is aligned with the main lobe of the typical receiver. The interference is pointing at the side lobe of the typical receiver. And then the interference and the typical receiver are pointed away from each other. We use a Nakagami amplitude fading model, which is a very flexible model, which can be tuned to either Rayleigh fading or as far as could go up to deterministic fading. And therefore, the power is going to be gamma distributed. The path loss intercept of mmWave is accounted for. The noise power is what we're comparing with. And then this is the random distance due to the PPP. And finally, we have the random blockage. So with some probability, a link is going to be non-line of sight, which will result in a path loss exponent of 4. And with some other probability, it's going to be line of sight with a path loss exponent of 2. So here we have the main quantity that we manipulate. We have the probability that a link is noise limited, which we set a threshold of T. So basically, if the INR is less than T, we consider it to be noise limited. So what we do is we manipulate this equation, and we treat this constant as a gamma random variable with a large n. So it's going to be a random variable with an extremely low variance. And what we can do then is we can approximate that gamma random variable in order to use stochastic geometry to analyze the results. So after some manipulation, our final result of the paper is that the instantaneous INR distribution of a mmWave ad hoc network can be tightly approximated by this equation. And what this is showing is that we have these 2 terms down here. And what this accounts for is when the interference is line of sight and when the interference is non-line of sight. And within each of these 2 terms is the probability of those antenna gains. So it kind of separates itself into 6 different interference terms, each with some contribution to the INR. And here are some results with varying antenna beam widths. So here we have the most narrow beam that we use. It's a 9-degree antenna beam width. And with 3 different densities. So we have 1,000 users per kilometer, 500 users per kilometer, and 100 users per kilometer. And as you can see, in pretty much all of the networks except for the sparsest one, the INR is, even with the extremely narrow beam width, the INR is such that the network is interference limited. And comparing that with a slightly larger beam width, we see that now that there is more opportunity for interference to get into the typical receiver, the interference curves are shifting even more. And we have the same densities again, 1,000, 500, and 100. And lastly, we have the CDF with 90-degree antenna beam width. So just a slight gain in the main direction and a slight loss in the side lobes. And here, pretty much, it is always going to be interference limited, even in the sparsest network. There's a very, very small chance, almost 1%, that the noise will be bigger than the interference. And now we compare basically line of sight interferes with line of sight and non-line of sight interferes. And what we see is that the network, when it is interference limited, is very basically line of sight interference limited, that the line of sight or that the non-line of sight interference is essentially negligible. So in conclusion, we derived an expression for the INR, CDF, and millimeter wave networks. Millimeter wave ad hoc networks can be interference limited, all but the sparsest networks with the narrowest beam width in that case. Line of sight interference is by far the most dominant, and that the aggregate non-line of sight interference is negligible. And that if there was some interference avoidance scheme, avoiding line of sight interference is likely worthwhile. Here are some references. Thank you. Break.
Okay, just give me a half a 30 seconds or so.